time schedule says that we have 4 speakers today, it's actually 5. So again, we don't have much time. Our first speaker is also keynote speaker, Professor Adam Sofka from Poland, and he's going to talk about chemistry-based method to assess bitumen quality.
Okay. So good afternoon. Like Carly said, I'm Adam Zofka. I'm coming from Road and Bridge Research Institute in Warsaw, Poland. My 2 co-authors of the papers are Miglė Palikuaitė. She's from Lithuania. She spent some time elsewhere as well. And my other co-author is Mrs. Agnieszka Woszuk. She's actually from Technical University of Lublin, also in Poland. So since we have 30 minutes, it's actually quite a lot for me. So I will do a little bit of really kind of like a lecture, just for some of you to be a little bit more familiar with the few methods that I am actually using since some time. I'm not a chemist, by the way, yes, I'm civil engineer, and I got to know some of the methods over the years as very useful in what we are doing in asphalt industry or in pavement industry. So I would like you to also not to be afraid of some of the methods, or to use them in a proper way, or to use them for what they are meant to be used. So in terms of the quality, as we listened to as we heard in the previous session in this room, there is a general agreement that there's something happened in the binder, in the asphalt quality in the recent times. And what might be the reasons are what we keep hearing from the refineries, although they will not tell us exactly, is the processing, how the asphalt or the crude oils are processed. Is the crude oils are also the resources, or eventually they are for fact they are changing. Yes, with every day probably they keep changing, or every other well, every other place. They are not the same as we know. Coming from different places, they have actually different properties, and they have a different feasibility to be actually eventually converted into asphalt. Some of them are actually not possible. And we have newer and newer methods in the refinery. And the 2 slides, two figures that you see, is actually the asphalt, some of the picture that is almost 100 years old, and some modern refinery. Although some of the maybe elements are not really different on these 2 images, but it still now becomes a little bit more complex process of producing the asphalt. And also what is even more complex is the blending of different crude oils, and that's what it's a common knowledge. I don't know this by fact, but getting the crude oils from different sources is also not helping the stability or the quality of the asphalt that is produced. And also asphalt evolved from what is called the byproduct, that maybe when it started 100+ years ago, it was just the byproduct of the crude oil refinery process. But right now it's really the product, the market product, that is governed by the economics. And sometimes this economics is more important than actually the properties or the engineering properties, at least from my perspective. And also there are different challenges. We have new modified asphalts that are newer. There are new additives added for a variety of reasons. Some of them they may help, some of them they may not. They actually may threaten some of the other properties, or they can affect in a negative way. But also we have the sustainability, we have the new big themes that we have to satisfy with our materials. And also the other part of the motivation is how do we check the quality right now? How do we check the quality? One of my favorite book is actually over 100 years old and talks about the asphalt pavements. And these pictures are actually from this book. And as you may recognize, is a version or the early version of the penetration method. And the book is actually this way. It's from 1920. It talks about the penetration, how it was developed in 1888. So almost 130 years ago, we used something, at least in Europe, yes, over and over again, as a check, one of the major, how we graded the binders or the asphalt. And it says here, the highlights part, that it was patented actually in 1889, if I remember or see correctly. So it's kind of funny for me that we are using something that is from 19th century, and we spend so much money as a societies for asphalt roads, and we use something that is over 130 years old. And the other pictures, you may still also recognize them from the same book. There are different methods that we sometimes use even these days, yes? Sieve analysis, some tensometer, or some small load press. So this is, we have to realize that these are over 100 years old methods. For me, it's kind of bizarre. And also in actually a little bit older book, I mean from 1913, if I see it correctly here, it says even over these days, it was, as you may recall, it was the rapid development of cars in our automobiles in general. It says somewhere here, also in highlighted part, that at that time, the asphalt pavements or pavements in general or roads were undergoing a major change, or at least they were supposed to, because of the new cars or new methods or materials, how they are actually used. And it's kind of amazing that they said this in this book. It was over 100 years ago, yes? But how I see on the pictures in this book, I mean, we didn't really progress much, yes? And how come, yes? We have this, already mentioned today morning, this new concept, yes? The automated cars and the track platooning, and we have different, you know, the electric cars, yes? And we, on the other hand, looking at the infrastructure, we're using something that is 130 years old. I don't know, I don't quite sometimes understand this, but I believe that we can do better, yes, with the chemistry-based methods, for example. So here are some of the, for example, images, and I will not talk about necessarily about those images. I can tell you the upper right-hand side is actually from the machine that is called the SEM, or the scanning electron microscope, and the other two are actually from the atomic force microscope that are typically, they are standard really methods in the material science business. What I would like to discuss for a while is the testing, the way how we do the testing, yes. We have really two options, yes. We can either do it mechanically, yes, we can evaluate the properties to get the mechanical properties, or we can look more closely into structure of the material and use some of the analytical or chemistry-based methods. Yes, we have two options to do. Most of the time we do the mechanical looking, which is already looking at the effect of certain things. So we cannot, or the phenomena. So we cannot really detect the phenomena, we can just determine the effect, what they are doing to the material. The other thing is to recognize we have the equipment or the methods that are more practical, research grade, or industry grade, or some of the methods that we have to use wisely, and they are more for investigating the properties of the material, which are the more like a research grade type of the equipment or the methods. Then we have to recognize that when we're talking about the development of the new methods, the new materials, we're talking about the science. We should not focus on some specifications or certifications or anything like this, yes? It has to be really free, unconstrained research, so science. So a little bit indirect and direct methods are already mentioned. So indirect, what I called, that we are looking already at the effect, and direct is to try to understand what are the causes of this particular effect. And also traditional versus modern, so looking at something that is already 100 years old versus something that is maybe a little bit newer than over a century. So one of the one of the methods to evaluate materials is based on the concept that is called spectroscopy methods. So it's really we should not be afraid because we use it all the time, yes, looking at the stars on the sky or looking at even here every day when you use the electromagnetic spectrum, we use only a portion of the light, yes. When we actually look at different frequencies of this light, we have the spectroscopy, yes, really how the light is interacting with different materials. So in principle, that's what it's done, yes, in the spectroscopy methods. You just direct or the light and the sample, maybe it's easier on this next slide, and then not just the light, but the particular frequency of the light, yes, in one of the regions, either X-ray or infrared or near-infrared or other, or yes. And then when the light is interacting, then there is some phenomena that is a clue to each of the different methods that we will discuss. This is the clue because each light or each frequency, there is a different phenomena that is happening in the material. And then we have some sort of detector, typically, when we look at what is coming out after interacting with the material. We have to measure, of course, we control what is going in, and then we have to measure what is coming out, yes, from the material. And then we record this or we interpret this into some meaningful information. Of course, each of these steps, it has a it is still, there are still some changes because this methods or the devices or some of the methodologies still evolving, yes? This is the part of the material science that they work on this kind of materials. We as engineers here, we should, let's say, use at least the ones that are more established, and then, of course, look for the new developments in these methods as they are approved or established with time, yes? So here are some of the examples. I will not focus on this slide because I have at least two of the methods from this slides. I will talk in details in the next slides, but these are just the examples that I was heavily involved in recent times. The FTIR spectroscopy method, Raman spectroscopy, XRF, and XRD. Yes. Each of these methods is really it's actually totally different and doing something totally different things, or measuring or observing different phenomena inside the material. Some of them are actually not suitable to asphalt due to its nature or the composition. Yes, but when we talk about the soils or we talk about the cement, some of them are actually perfect for these materials, but yes, so there is some knowledge behind which method is better or more suitable for what material. But this information is out there, yes? It's not a secret, really, which method is good for what. So when we can we can talk about first the thin layer. I didn't do anything. So this is not my presentation. Okay. Oh, this is my presentation. A little bit up. Slide number 12. So when we start with not a typical spectroscopy method, but we talk about the chromatography, yes, it's a little bit different part of the analytical chemistry. When we are looking really at it's like if I can simplify this, we look at like a sieve analysis for our material. In this particular case, I will talk about the asphalt, yes. We do the sieve analysis, so what is inside our asphalt, what is bigger and heavier, what is lighter, what fractions, yes? As you may remember or know, we have this Sara fractions, yes? In asphalt is composed, or at least in some theory, is composed of the 4 fractions that we can separate or we can detect using the chromatography. And in this particular case, we use a particular type of the chromatography because there is I don't know, tens or maybe hundreds different ways, different chromatography methods, maybe tens of different. But in this particular case, I will show you a fairly simple device. Anyway, it's a thin layer chromatography, flame ionization detection, which means you take a small piece of sample, maybe of asphalt. Maybe I will show you this on these figures. You take a small amount of asphalt, binder, which is really less than fractions of the grams, and you dilute it with the toluene, or maybe in other methods, in other approach, different solvent, and you put it on these little rods that you see here, which are called chrome rods, and then you put this into this kind of like a frame, and then you put this frame into 3 different solvents sequentially, and these solvents, they have a different polarity, and due to the capillarity forces, then this asphalt that is diluted on these rods is actually going up to different levels, and the levels depending on the fractions or how heavy is the particular fractions inside the asphalt. And once you have this, then you put it in this on the left hand side, this machine, and you burn it, really, yes. Without the oxygen, you burn it and you detect the flame. That's why it's called the flame detection method, FID. With this, you can actually obtain, if I can go back a little bit slide, you can obtain the spectra that is on the bottom of the slide that will show you most of the time 4 peaks for unmodified binder. And if you calculate the area with these peaks, the area is proportional to the content of these fractions inside the material. So it's fairly easy method. Of course, it's the devil is in the details. There are, of course, some details that you have to work, and there are different approaches even to this particular methodology. There are a little bit different approaches depending who is using the device. But in general, the general consensus is that it can give you the Sara fraction, and the Sara fractions are related to the performance of the asphalt. Yes. So if you didn't do this exercise, there are in the original Sharp study in the United States, they actually measure the Sara fractions, of course with different method than this one, but they do measure them. And then they build the pavement sections with these different asphalts, and then you can try to correlate how these different fractions, how they affect, assuming that everything else stays the same, but you can assess how they affect the performance of the payment sections. And here are some of the results. And I apologize a little bit for this slide, but in general, what is happening on this slide, this different variation are for different asphalts. The fractions always sum up to 100, but the variations are because of the aging process for different actually binders on this figure. If we need, in the break, I can elaborate more on this figure. And now I just want to move to the second method. So in the chromatography, we talk like about the SIF analysis. Here in the FTIR, we look at the molecules, or the individual molecules, and we know there are hundreds, if thousands, if tens of thousands, of hundreds of thousands, according to some people, different molecules in asphalt. So how we can actually measure them, but we don't measure all. We know that due to certain phenomena like aging, we can expect some of the growth of certain functional groups in our material. So when we observe these particular regions, which are very well established, or according to some of my colleagues, you can actually calculate them if you are smart enough, where they should appear, then you can actually observe the different sensitivity of different asphalts, for example, to aging, and see how these functional groups are growing or not, or how fast they are growing. So you can detect the functional groups like the carboxylic acid or ketones or sulfoxides, and they are all related to a particular place on a spectra. So to understand a little bit more how it's actually FTIR is measured, it's you radiate the material with the particular infrared of light, so which means the frequency is controlled by the machine, of course. And then the molecules, they absorb some of this light. And then when you can actually, on the detector, you can measure how much of the material was actually, not the material, how much light was actually absorbed by the material. And then you can plot it in the spectra. So you will plot on the amount of the energy absorbed versus the frequency. And the pictures of the device here, you can see different devices. You can actually do the testing on a site, on the construction site, and then at the end you will get a spectra that is on the lower picture. And the problem a little bit with this method is that this absorption of the light by the molecules, it's causing the vibration of the molecule bonding. And this vibration, there is a whole theory that it can cause stretching, bending of the bonds, or it can be symmetric, asymmetric. There is, at least at the beginning, there might be a little bit overwhelming information. How many, you can see here from the SHARP report as well, you can do what type of molecules you can, like classical molecules you can recognize in the asphalt. And some of them, they actually have very well-defined locations where they should appear on the IR spectra. Like here, you will see also that these are actually the frequency on the left-hand side along the y-axis. So you can see also some overlapping. So sometimes if you actually add some additive that is, for example, overlapping or partially overlapping with one of the well-established regions in asphalt materials, the interpretation might be also challenging, yes? But in general, this is not a case, at least for regular applications of the IR. And there is a little bit different methods of the IR. I will not go into details of this. You can do it in a transmission mode, typically, or attenuated total reflectance, and they are actually depicted on this figure, and they are also in the paper. Plus, you can use diffuse reflectance. The sample preparation is very simple, at least in the ATR mode. And you just put the sample or asphalt, you just stick to the window, a little bit small window, 2 by 2 millimeter, and you just do the measurement. So what you can actually see here, there's some of the examples. you can see the growth on the y-axis. In most of the figures, you can see the growth on the sulfoxide or the carboxylic acid, which are the products of the asphalt oxidation, as we progress the aging here. On the x-axis, you will see either short-term aging or short-term aging plus long-term PAV or plus double PAV, for example. Yes, you will see this growth in each case. And the last method is the XRF, X-ray fluorescence spectroscopy. This is to determine different particular individual elements. So first, in the chromatography, we had like a SIF analysis. Then in the IR, we have functional groups. And here we are looking at the individual elements of our material. So if we know what should be there or what not should be, or what not should be in the asphalt, then we can use the XRF. And here, as you can see, the examples are using this in the PPA, or polyphosphoric acid, with the polyphosphoric acid modifications, or with the REOB, so recycle engine oil bottom modifications, or cramp rubber. You will also see it in the asphalt. So in the previous slide, you could see you could detect XRF everything from sodium to uranium in the periodic table, and how it works really when you actually direct the X-ray light with the X-ray frequency at the material, the atoms will change the energy levels. And when they change the energy levels, they emit fluorescence energy from them, and you can actually measure this, detect this radiation of this fluorescence waves and the intensity. When you have both the radiation and the intensity, you can actually tell what elements are there and how many of them is there. So this is both qualitative and quantitative method. So here, just to show you the example of the device, this is actually like a stationary device. With the carousel, we can put multiple samples, and you will see here the schematics of jumping of the electrons actually from one energy level to another. And then this is also the example of the portable device that was actually shown in a similar device was shown in one of the previous presentations in the previous session. And this is the example, how you can look. We look at the calcium, copper, zinc, and molybdenum here, and you will see that when we compare the regular asphalt, which is the second from the left, and when you compare this with the 100% of REOB, and I just pay attention to the logarithmic scale on the y-axis, so really there is no mistake. If there is 10,000 ppms in regular asphalt for calcium, then you have over 10,000 in REOB. But when you start mixing the REOB and the asphalt, then you will still detect different concentrations of these elements that should not be in this concentration in the regular asphalt. Yes, there is no other cause that they should be there. Okay, just almost finishing. We have also other methods. You may hear them when you go to different conferences, and maybe some of them, they were mentioned or they're going to be mentioned here in this conference. You have ultraviolet spectroscopy, you have NMR, you have MS, you have TGA, DTA, you have a different chromatography method, you have a SEM and FEM. And so they are actually, some of them, most likely they are overlapping, but most of the time they have a very specific use, at least how we use them in asphalt industry right now, yes? Or asphalt research. And if you need more information, of course, there is a bazillions of papers, but what I found recent, actually, I want to show you two recent reports. One of them is this one. The other one is that I have to show this one because I'm a co-author or main author of this. which was using the field spectroscopy devices to check commonly used construction materials. Which method is good for which material, going from the cement, asphalt, soil, paints, and all of this, epoxies. So in summary, in my opinion, we use more advanced methods to assess our quality of our asphalt and study its complex composition. We need, as I mentioned before, these techniques, they evolve, and they are actually very small these days, very accessible. It was not the case like 30 years ago. Some of these devices, they were the size of the room, or they were not even existing because the technology was not there. And the road owners, of course, they demand effective and durable materials because we expect the future, the change in our transport, yes? And also, and what I wanted to say, sometimes the civil engineer is not enough. We should be more like an engineering scientist these days, yes? Because we should understand also a little bit of the causes, what is happening with our material. And it's like this, we drill the pavement, for example, and we just measure this dust. And you can do it actually with the FTIR, yes? So no more cores, like 150 millimeters, yes? And just going back to this caveman that I forgot to mention on my first slide. So what I wanted to show, we just need to know how to use the right tool to the right job, yes? The right application, yes? Because this caveman, he knew that he needs to use the hammer. The hammer evolved over the years, so he understood the concept, how to use the hammer. He understood how to use it, and we still use the same hammer, yes, which was okay in this case. But maybe with some of the tools that we use these days, it's not necessarily the case anymore. Okay, thank you.
Thank you, Adam. Since we don't have much time, the buses are leaving at 17:40, so you have to move on. So no time for questions. Our next presentation is from Latvia, Andris Palodis, and he's going to talk about using image processing in order to determine the adhesion between bitumen and aggregate.
Hello, I will try to be short. So, let's move on. The main aim of the work was to improve the quality of adhesion test between bitumen and minerals. As we know, it is very important to get a good adhesion between mineral and bitumen. So that means it's important to measure that very precise. The idea wasn't mine, the main idea. I took it from one work which was made by guys from Italy, Riccardo Lamperetti, Claudio Lanteri, and other guys. They try to do something like I did, but I try to do it more precise. They had some precise things in that. So I used three kind of different minerals in different colors: the dark granite, red granite, and pale dolomite. And I mixed it with bitumen 7000. The specimens were prepared by the standard. You can see in the pictures how I actually did it. So for the processing, I used the program ImageJ. I selected it because those guys from Italy, they use it too. So I thought I will try with this, and it will, if it will be bad, I will try with Photoshop. But I used this, and I was satisfied because it was very easy to use. So I stayed with it. On the picture on the right, you can see my self-made photo studio. Actually, it's pretty simple. There's only 2 lamps, boiled with the water and with the specimen in it. And on the left, you can see how does this picture look after I took it. As I said, those guys from Italy, they had some unprecise things, and the main 2 problems was shadows from the minerals and this reflection from the lights. So I tried to remove them, and I actually did it. I just soak in my specimen in the water, so that helped me take off that reflection, and I put up this boil with water and specimen up to 30 centimeter from that green background. And it actually helped me take off that shadows. But I tried to calculate this coverage of bitumen with photo processing method for fully coated minerals, and I calculate only 97% coverage. So that means I had somewhere 3% loss. And I think it's we can see there's a little spot from reflection. So I took this factor in calculating too. Here you can see how I work in this program. Actually, it is pretty simple. We're just regulating 3 things: hue, saturation, and brightness with the regulators, and with them we are separating the white spots from the black spots. No. So here you can see how I already separated the black spots from white spots, and down here we can see the calculated area which we need to know. Let's talk about calculations now. So to calculate the coverage of bitumen, we need to know 3 areas: the whole area of photograph, the green background area, and the total area of green background and spots which are covered with bitumen. If we know those 3 areas, we can calculate the main coverage of the bitumen. So the results. I tried to take the photos in the two different types. The first type, I took a photo, then I turn around each mineral and take a second photo. And the second type was I just mixed the mineral, the specimen, took a photo, mixed it again, and took a photo. So the purple beam is the average result from 3 operators for those first side and second side. The green beam is from mixed specimen, and the beige beam is from visual processing. So as we can see, for the dark granite, the difference isn't big. For the red granite, the difference is bigger. It's about 7% between visual method and photo processing. The photo processing method shows us a lower bitumen coverage. And for the pale dolomite, the difference is the biggest. It's about 10%. And it's a significant difference. So after those 3 specimens, I get some conclusions. The first, in general, the photo processing method shows us a lower bitumen coverage. Is it closer to the truth? I don't actually know. We need to explore it further. If the aggregate is lighter, the photo processing method shows us a lower bitumen coverage. As we saw for the dark granite, it was simple, pretty we are not. Pretty same. Yeah, and both image acquisition methods are equally correct. As we saw for all 3 specimens, there was only 2% difference between those two types of taking photos. And the photo processing method still needs some improvement. It's sure, because as I see it in the future, we will have only specimen, put it in a boil, then press some button, and after some few seconds, we will have some result. I think it's a visual method. It's too old. We are moving forward. It's 21st century. We have some good technologies, and that's what I did. It's only one step, so we got a lot of steps to do further. Thank you.
You gained us additional 5 minutes, so thanks. Any questions, anybody? So, thanks. Our next speaker is Martin Saumanis from Latvia, and he's going to talk about when and where to add rejuvenators in the asphalt plant.
Thank you. He was my colleague, so I will take his 5 minutes for my presentation, if that's okay. I can see it here. First of all, what is a rejuvenator, right? Maybe I'm working with it every day, but not all of you do so. So I'll quickly go over why do we need a rejuvenator at all. So first of all, when we mill the old asphalt, that's mainly because it has aged. There are some potholes, the binder is getting stiffer, so we need to mill it and we bring it to the asphalt plant. We can reprocess it, we can screen it, we can crush it, and so on. Of course, we have our virgin materials, and by combining these two in a certain mix design recipe, we can produce a new asphalt mixture. Well, if you add a little bit of the reclaimed asphalt, let's say 10–15%, you don't really have to care about anything. You just use your mix design recipe as it is. If you add a little bit more, let's say up to 30%, you already need to start thinking about how to compensate for your aged asphalt binder. So in this case, you might be well off by adding a softer binder grade. So if you normally use 50–70, maybe by adding 30% reclaimed asphalt, you should switch to 70–100. But if you go higher than that, you really don't have the capacity to add the softer binder grade anymore. First of all, it's not going to be soft enough, because in your region, you probably cannot get a very soft binder. And second of all, your mix design recipe will simply not allow to put as much binder as you need in there. So in this case, we can use rejuvenators. And obviously, we want to pave and use the mixture as a normal road as we would do normally. So a rejuvenator is a sort of oil. It's not really rejuvenating it, rejuvenating the binder chemically. Otherwise, we would be using it on our faces and be forever young. But it does provide us the mechanical performance of the bitumen that we want for another service period of the pavement. So we want some softening effect, we want to regain the elasticity of the binder, and so on. The types of rejuvenators, they can be different oils, starting from, someone mentioned here, the waste engine oil. It could be a refined oil, it could be vegetable oil or pine oil or whatever. There's no real definition at the moment. Well, now the problem. If we have an aggregate and we have it covered with the binder film and we apply a rejuvenator on it, right? Now the rejuvenator is covering the binder film from outside. So in order to blend together, it has to first diffuse into the old binder film. And that's not really so simple, because the diffusion and the mixing process will depend on the aging state of the old binder. It will depend on the rejuvenator. It will depend on the temperature that we're using in the mixing plant. It will depend on the time of the exposure to temperature. So there are all these factors that affect the result. And the result will, in most cases, be blending or this binder activation somewhere between 0 and 100%. We probably will not be able to activate 100% of the old reclaimed asphalt binder. This is an image we took in another project. We replaced a portion of the filler with a tracer with an titanium oxide. And you can see that the tracer is everywhere except on a very thin binder film around the wrap aggregate. This means that basically we are not reaching this binder. Although it's there in the mixed design calculation, we would consider it as binder. Actually, it's more likely a part of the rock instead of being part of the binder. So obviously, as a mixed designer, as an asphalt producer, we want to maximize the portion of the binder that we are getting from the old wrap, because that's the most expensive portion. It's the portion that provides elasticity, it resists cracking, and so on. So we want to maximize this part. So the question is how to do it the most efficient way. Of course, there are different rejuvenators, different plant technologies, but one thing that we have to decide is how to add the rejuvenator. So the normal way, or the traditional way that it's done, is usually after heating of the reclaimed asphalt, in the mixing or the pug mill, the mixing drum, there's an additive dosage system. So we can add the rejuvenator there. Sometimes it's also added to a virgin bitumen. This would be kind of creating your own soft binder grade. But who is to say that we cannot add it earlier, right? The longer the rejuvenator is in contact with the binder, the more diffusion we will have, the more binder we can potentially activate. So we could add it to the old asphalt before it's being heated, so the cold reclaimed asphalt. We could add it even earlier when we're processing the material, and even maybe during the milling operation. We actually went ahead and we counted that there are potentially, theoretically, 10 different locations where we could add the rejuvenator. So you see the blue ones are upstream of the recycled dryer drum, and the kind of yellow ones are downstream of the dryer drum, and the purple ones are in the virgin bitumen line. Okay? In this example, somewhere where number 3 is, those are the cold storage bins, then the material goes up in the tower, it's being heated there in the hot mixer, in the hot dryer, and down in the tower there's the mixer. What we want from these different options is not only the maximizing of binder activation. We, of course, want it to be environmentally safe, so we have to check what are the conditions that we can make it safe. And some of the options are disqualified right away because, for example, we don't want the rejuvenator to be leaking into the ground, so we cannot really add it in the stockpile. Next, we want to be sure that it is technically possible to add the rejuvenator somewhere in the plant to control the dosage and integrate in the plant system. And finally, we, of course, want the mixture to have the quality, and the rejuvenator to be precisely dosed, the resultant mixture to have its properties as we designed, and so on. So, at the end, based on this kind of theoretical calculation, we saw that there are 3 different options. 2 of them are quite similar, so we decided to focus on 2 of them, and we went ahead, actually, in asphalt plant, and we tried these 2 different options of rejuvenator addition. So one of them is adding the rejuvenator after the reclaimed asphalt binder has been, reclaimed asphalt has been heated in the mixer, right, that's somewhere here. And the other option is to add the rejuvenator to the cold asphalt right after it's leaving the cold storage bins on the belt. So here we are able to control the dosage based on the volume of the material. Okay, so that's here. Now, we have 2 additional locations, but I actually have five different places to take samples. First of all, I have just a wrap sample. We took it before adding the rejuvenator. Next one, right after addition of the rejuvenator to the cold asphalt. And you can see in the letters, it means we sprayed the rejuvenator, then we, on a cold reclaimed asphalt, and we sampled the mixture cold. Next, the same sample went through the heating drum, so we sampled it hot. Next, we sampled a reclaimed asphalt that was heated without any rejuvenator. And finally, we had a sample where the rejuvenator was applied hot, and it was sampled hot. I know it's a little bit, a lot of information to take on, so if you feel like sleeping for a while, that's fine with me. I'll wake you up in the conclusion section. That's going to be very easy, I promise. So now I have my 5 different addition spots, and I wanted to have 3% of rejuvenator dosage at each of these spots. Unfortunately, since this is a real life, this is a real production process, the reclaimed asphalt binder content varied. So although my dosing was the same for each of these cases, since the reclaimed asphalt binder content varied, then obviously my proportion of the rejuvenator also varied a little bit. So instead of 3%, I got somewhere between 2.6 and 3.1. That would be fine for actual production process, but since this is a research study, I had to somehow take this into account. So what I did is I took my samples that were sampled hot, the one without any rejuvenator, and the one where I added the rejuvenator in the mixer, and these are kind of the baseline. So I know that these are the same. The only difference is that the rejuvenator content is different. So for one of them is 0, for the other is 3.11%. And if I connect them with the line, so I can say that if the only difference between any of my samples would be the rejuvenator dosage, the samples would align on this trend line somewhere. If there is some other effect, like aging in the drum, like losing of some rejuvenator, whatever, the result would not be on this line. As we can see, the penetration difference between this line and the different samples is actually very small. It's about 1 to 2 decimillimeters. That's nothing, considering that we did all these steps, producing, extraction, measuring, and these things. So I can say that based on penetration, the addition spot didn't make a difference. Next, softening point, and basically the same idea. Again, the results are almost on the trend line. Next, we did use the dynamic shear rheometer, which to build a master curve, which is basically the stiffness and elasticity ratio at different frequencies of the reclaimed asphalt binder. And of course, we can see, the stiffer the material, the higher the master curve would be in this graph. And of course, we see that the reclaimed asphalt binder, where we don't have any rejuvenator, the lines are higher up. When we have added the rejuvenator, they are lowering, but we again see that they are lowering to the same extent whether we added the rejuvenator to hot or to the cold binder or wrap. And finally, Professor Zovka already explained the Fourier transform infrared spectroscopy. This is what we use to evaluate chemically the differences. And these are the 2 functional groups, as he explained, that represent aging of the binder. So sulfoxide group and carbonyl group are the ones that increase. The area below the curve increases when the material ages. So, as I said, we didn't see any reduction of these areas. That's because we cannot rejuvenate, really, we cannot restore the chemical structure of the aged binder. But what we wanted to see is whether, based on our addition spot, the area increases for one or the other case. So to do that, we can plot the area in a chart as an index. And if we focus only on the green line, this is the combination of these 2 areas. We see that First of all, the second kind of group, the spray CH, which means that we spray the rejuvenator on a cold asphalt and sampled hot, is basically the same, has the same index as the mixer HH, where the rejuvenator was sprayed or added in the mixer and sampled hot. So there has not been additional aging due to addition of the rejuvenator before the drum. Okay, so now the conclusion. And it's very simple. The rejuvenator addition point did not make any difference with respect to the binder properties. So regardless if we added it to cold wrap or to the hot wrap, the effects were the same on the binder. It took me quite a lot of effort to find this out, right? We did produce in an asphalt plant tons of mixes, tons of asphalt mixture. We did all this extraction work and testing. But actually, the conclusion that we don't see any result or any difference is a good one, because we know that it's not worth to add the rejuvenator before heating of the wrap. Whether it's better, I cannot answer at the moment because we haven't done any testing on the mixture. So as I said, when we extract the binder, we blend all the materials together. So in this case, we kind of artificially assume 100% blending, which is not what happens in the real world. In the real world, there is probably a little bit less blending, and that we have to find out by testing asphalt mixture. That is what we intend to do. We have already gathered samples, and we will perform the testing on asphalt mixtures. In addition to that, during the production, we measure the emissions, so that concerns the first part of the evaluation, where I said it has to be environmentally safe, both to the crew and to the environment, with respect to pollution. So, thank you very much. With that, I will conclude.
Thank you, Martins, for your presentation. So any questions to Martins? No? So, thank you. Our next speaker is Priit Vilva from Estonia, and he's going to talk about the trial concrete section in Tallinn.
Ladies and gentlemen, dear participants, first of all, I want to show you one video about constructing of this concrete cement road in Tallinn. And after then, we have, of course, less time, but I can briefly focus for some details and aspects what are important. As you know, the devil is hiding in details. And okay. Okay. I think for somebody, of course, it's a trivial story, but this story belongs to the more applied science and experiences. And why concrete pavements in Tallinn? No, here is some important issues why we decided to build concrete pavements. The most important reason was, of course, to get some real experiences. But as I said, the devil is in details. And of course, concrete pavement is more suitable for urban situation because in urban situation we have more static loads, cross bus stops, public transport lanes, and etc. This decision was made in 2013, and this project was implemented in 2016. 3 years took this project. And of course, the next step for us is monitoring of this experimental section. I think it takes about 5-6 years and consists of several issues. Of course, maintenance situation, measuring of temperature gradients, traffic flows, and laser scanning of the surface of the pavement to determine route development. And conclusion, if we have a good results, then idea to set up the next program of constructing concrete pavements in Tallinn. The concept of construction of experimental section was to use existing asphalt concrete pavement structure and combining it with the new pavement construction in widening paths, as you saw in this video. And of course, we done geotechnical investigation and bearing capacity tests of substructure. Then we control the level of groundwater. It's very important for this frost eve resistance question. And the frost depth in this region approximately 125 centimeters. And as I said, property of soils and existing pavement substrate materials are suitable for requirements in terms of bearing capacity and frost heave resistant. Construction transversal joints were cut at distances of 4.5 meters, and longitudinal joints, the slab width is 3.75 meters. Of course, they were joints were doubled, and longitudinal joints were joined with tie bars. This location scheme of this section of concrete pavement is near of Lake Arku. One is the main road of Tallinn. What we are interested about is a design method, and we use this current Swedish design method and combining it with additional aspects of German and Dutch design methods. And the most important issue is use this minor Malmgren damage hypothesis for flexible stresses. That's the base of this designing method. Here is this well-known formula. And about this traffic, of course, this designing of concrete pavement is must use this data about traffic. Traffic is average annual daily traffic is approximately 18,000 vehicles, and the total number of estimated equivalent standard axle load per 40 years is 23 million. What is interesting for us, of course, how to evaluate this substructure reaction key. As you know, key is depending, has a functional connection with the deformation modulus EV2, and here is, in my report, I have brought to you these formulas. And for bound base, there is impossible to use bearing plate test. Then we used falling weight deflectometer and evaluate this elasticity modulus ED. And ED is a dynamical E module, and connection with this static modulus of elasticity is brought here. And K can be expressed through this formula. One most important issue is, of course, temperature gradient. We used Swedish data about these temperature gradients. And of course, in this project, this raises a question about our situation, but we were very conservative, and we use Swedish data, and the temperature gradients took 60 degrees Celsius per meter with 20% of the year time. And to get accurate temperature gradients for Tallinn, we started this temperature measurement program by the Bergo station system, and there are 4 sensors in different steps: 12 centimeters, 25 centimeters, 42 centimeters, and 100 centimeters. Some illustration about this Bergo station. And one example, we get in actual time, after every 2 hours, the temperature situation of this pavement. And after 5-6 years, we can do some conclusion what's the more accurate temperature gradients situation in Tallinn. And as you saw, the experimental section consists of 2 parts. One is the plain joint concrete pavement with slab thickness 25 centimeters, and the second one is plain jointed concrete pavement with slab thickness 20 centimeters and covered with asphalt, stone mix asphalt 5 centimeters. This for illustrating 2 versions of these cross sections. Some well-known pictures about this making process and monitoring program. So 5-6 years. Regular observing of maintenance situation, cracks appearing, joint situation, and etc. As I said, plus temperature gradient measurements by Bergo station, groundwater level measurements by special well, and laser scanning of the surface of the pavement and data treatment. The reason is to determine the settlement and unevenness and blowouts of pavement, and determine a route depth development depending on traffic frequency and cost. Some example illustration about these laser scanning results. very important question, of course, is cost question, life cycle cost of concrete payments was analyzed in Tallinn University of Technology 2015, but using this experimental section we have a possibility to correct these results, and the results are here. And what we find for 40 years, this will be cost less 15% compared to asphalt payments. That support the same investigation what we have heard in Poland, in Czech Republic, in Lithuania. And conclusion, of course we need more information to make the new decisions, experiences and research. But most important issues, of course, we must create our local Estonian mixed design and using our own Estonian cement and avoiding alkali-silica reactivity with aggregate. That's the main questions. To determine substructure reaction modulus in existing payment is a true very interesting issue. And as I said, temperature measurements to find accurate temperature gradient. And to improve, of course, traffic estimation in design measurements of load, axle weight, and maybe to have a new correction of this adjusted coefficient for several tires. Now here is one famous guy from Estonia who is has a big experiences, has built many thousand kilometers of beton concrete, not in Estonia, but in Australia. Thank you.
Thank you, Priit. Any questions? So, thank you. Our next speaker is Mr. Rieks from Latvia, and he's going to talk about heat transfer in unbound layers.
Hello, my name is Carlos. I'm a PhD student from Norwegian University of Science and Technology. First of all, I have only a poster. It was up until tomorrow, I didn't know that I will have to make a presentation, actually. Yesterday, I found it out. I was like, okay, I can talk 10 minutes about this topic, but I don't have a PowerPoint to show you. I will use the poster just as an example, but I will mostly, I guess, describe the project that I'm working on and explain why we are doing and what we are doing. I'm also Latvian, and that's probably part of the reason why I'm here. I graduated from the Riga Technical University, and then I moved onwards to Norway to study my PhD. So the history about why we are doing this project. The project is called Frost Protection for Roads and Railways. Shortly, it's like that. The last sophisticated study on this topic in Norway was done around 4 years ago. It was done at a time when the major material used in road construction was natural mineral materials, as sand and gravel. During the last decades, few things has changed. Believe it or not, these natural mineral resources in Norway has been depleted. They're really scarce, sand and gravel. They mostly use it only in concrete, a little bit, I guess, in the asphalt layers. But now they mostly use the crushed rock. There's no problem of the rock, really good rock. They export a lot of granite and gneiss and so on. So it's just a matter of crushing the material. But the thing is that actually the characteristics of these two types of materials, so of the natural ones and then the crushed ones, are pretty different. The main difference is from the fact that the particles are rounded for the natural materials and angular for the crushed rock. So, and because of that, you get different characteristics mechanically and also thermally. I usually feel like a minority speaking about this topic because, as you can see, most of the presentations is related to the mechanical design of the roads, of the stiffnesses of the materials and how they perform. Most of the things are related to strains, and then you relate it further to fatigue problems and rutting and so on. That's the typical road design based on mechanical approach. But in northern countries, and also including, I guess, Lithuania, Latvia, and Estonia, the winters can be pretty severe, especially in the inlands. Important thing is also the thermal design of the roads. Once you build the road on frost-susceptible soils, as clays and silt, and it happens, not always you can excavate all the material and put something else which is non-frost susceptible. Sometimes these materials are kind of stable if they're well consolidated. It's okay, but it's okay in terms of mechanical stability, but in terms of thermal stability, it can be pretty risky to build on top of these materials if the frost will penetrate into these silts and clays. Once the frost penetrates into the silts or clays, you can have frost heave. Nothing can basically stop the frost heave. It will just lift up your road. The road will get bumpy. It's less risky about the roads always. That's why we have also on our project the railway administration is involved. Because once you have this alignment for the rails, if you have a high-speed train going there, you need to. And if you start getting a frost heave problems, the rails are disaligned, you have to drop the speeds significantly. So my part in the project is about thermal properties of materials. Everything starting from fine materials, also the clays, and going up to really coarse materials. In Norway, they use much coarser materials than Baltics, I guess. Sometimes the particle size, like for example, a typical subbase is from 20 millimeters up to 120. So pretty big particles. So when it comes to this research, can you zoom in into those two pictures? So what do we have in the project for the thermal studies? We have a small-scale experiment, which is only for the thermal conductivity. It's not showed here. This one is a large-scale experiment. So the sample size is around 1 cubic meter. So there's a huge box, which is filled with materials. This in particular was a kind of a trial study. We filled the box with cobbles, which is not the typical road construction materials. We did it, the purpose of doing that was that we have some other data that we can compare what's going on. So the material is put inside a box. On the right-hand side, you can see those are heat flux devices. So they're measuring the energy which flows through the sample. Different temperatures are applied at the top and the bottom. So what happens? You can have two different ways of the direction of the heat. So basically, when the heat is moving downwards, it represents the kind of the summer conditions when the heat is stored in the ground, and when the heat moves upwards, so you have, in case of the box, you have hot bottom plate and cold top plate. It represents the winter conditions when the heat is extracted from the grounds. This test, it explains different mechanisms of heat transfer, what can occur for these coarse materials. The most typical mechanism of heat transfer is the thermal conductivity. That's for every material that happens everywhere. Now, if if you slide a bit down to this graph on the right, so the graph which is in the center. So this graph shows different types of heat transfer. So basically, the dotted line, okay? So the dotted line represents the thermal conductivity, which again represents the summer conditions when the energy is stored in the ground. The thermal conductivity is the slope of the line. So if you multiply the heat flux, which is on the y-axis, by the temperature gradient, you can calculate the thermal conductivity for this particular material. And then the dashed line represents the winter conditions. When the ground is warm, relatively to the temperature of the air, the heat flux is significantly increased. So for each temperature gradient on the y-axis, you have significantly higher heat extraction rate. The reason for that is that there is another heat transfer mechanism going on during the winter time, which is convection. And it's natural convection. If you don't know what it is, the simplest explanation would be when you turn on the heater in your room, the air gets warmer above your heater, it loses its density and it starts rising. And consequently, the cold air from the top of your room goes down because the density of the cold air is higher. So the same thing happened in the ground as well. Convection can form in terms of kind of an air rolls, and it's a fluid flow in this case. But whenever there's a fluid flow, it takes with itself a kind of a portion of the heat as well. Every particle of the air takes some portion of the heat out of the ground. So, and therefore, during the winter time, you can have much higher rate of heat extractions from the ground. A normal thermal design takes into account only the thermal conductivity. So that's what's typically been done. And in this case, if you have coarse materials like these, you can have coarse crushed materials as well. So if you're going to neglect the fact that there is a convection in these materials, you will underestimate the frost penetration rate, what happens in your materials. After we did this test, we have tested also crushed materials as well. Also this kind of a typical sub-base material what they use in Norway, which is without the fines, and you can have convection also in that materials. I know at least in Latvia they use finer gradations, but they produce also materials without the fines. The railways usually the typical ballast material.